Ever heard of forbidden transitions? Welcome back, everyone. Today, we get to explore how the electric dipole moment operator sets the rules and why quantum states remain elusive. For example, here's some pictures that I found about the electric dipole running from negative to positive, indicated with the red arrow, and how it migrates under the transformation of parity and translation. And we get quite a bit of ruckus here. And as you might imagine, these go against or have selection rules based on the violations they have. Another great example here. But without all the chatter, let's dive in and see what we're tasked with doing. So in problem 6.13, which is the last one we're going to cover in the parity section before moving on to, you guessed it, rotations. And the next big block of stuff will be rotational selection rules. But for now, what we are asked to do is to consider an electron in a hydrogen atom, show that if the electron is in the ground state, remember NLM equal 100, then it is necessarily that PE, the electric dipole moment operator, equals 0. Okay, that's the expectation value. And of course, no calculations allowed. This should strike you as, okay, time to use the selection rules. B, show that if the electron is in an n equal 2 state, then the expectation value of PE need not vanish. Give an example of a wave function for the energy level n equals 2 that has the non-vanishing expectation value and compute it for this state. Okay, there's a lot going on, a lot of words that he gives us in this question, but the goal here is that we want to showcase that some energy levels have the selection rules apply inherently due to their construction, others don't, and we need to find an example that we don't. But again, why do we care? These selection rules are very important and they can help govern the interactions. In fact, non-vanishing matrix elements of the electric dipole moment operator are essential in quantum mechanics because they govern the probabilities of various radiative transitions, determine the selection rules which we saw, and influence the polarizability and interactions with external fields. Again, all these little things coming together, and you may remember how the the electron's dipole moment, magnetic dipole moment, was such a big breakthrough. They all play together in this kind of weird weird dance of parity and rotation selection rules. Okay? So with that, let me give you a challenge and think about or comment an application of the electric dipole moment or of these selection rules in general. Because these matrix elements bridge the microscopic quantum world with the observable macroscopic phenomena. Think of all the radiations that we've dealt with, or Raman scattering, things like that. They all come together in a very nice way. This problem is kind of lengthy insofar as the calculations, not necessarily the theoretics. So with that, be aware that the PDF is available for you to follow along. It'll just clean up all the little nitty gritty that's too much for a quick video. So go see that. And I'm going to try something new and state this now. If you find value in this content, please consider subscribing, sharing with a friend, or donating through Buy Me a Coffee. No membership or account required. Alrighty, so stop number one then, as always, we need to get some definitions down. And the electric dipole operator is defined as P hat E equal QR. Now, in the book, he had a hat vector on it, as in it's pointing in the hat direction. But after referencing things like Griffith's chapter 3.4 in his Introduction to Electrodynamics book, this is a better way to write it, and we'll see why that matters later. But just be aware, boldface, hats, things like that get mixed up all the time, especially when we're trying to showcase that a hat here in quantum mechanics represents an operator, not a unit vector. So I took that hat off of what he put in the book and just left it as a vector for that reason, because the hat in the quantum mechanics book references a vector operator, not a unit vector. So just be aware, notation might be a problem there. But From there, we see that we once again, in order to find the expectation value, we sandwich this operator between two states, which recall in the hydrogenic orbitals, psi in and out in Lm is just represented by the ket, much easier. And by doing so, we find that this is a matrix element now, and thus we can apply the selection rules. No big deal, we've seen this enough by now, but be aware that that is the way to do this. And so when we're looking for an electron in the ground state, or psi 1,1 of r theta phi, we just write it as the broad ket of 1,0,0. Cool, no problem. Let's see how the selection rules apply this and what we can conclude. So the real question that we need to ask ourselves now is, do they have the same parity? I.e., does L plus L prime equal an even number? And in this case, we clearly see that both L's are 0. 0 plus 0 gives us a 0, which again is an even number, or at least not odd. We'll let the mathematicians debate that. But we see that that is an element of 2z for any integer. Cool. That being said, based on the selection rules, which in this particular case, because it's the electric dipole operator, we have Laporte's rule, and that is something that comes up all the time in the chemistry world. Very important for you to have if you're in chemistry. But the bigger picture here is that because this rule is now implemented, we know that this has to be 0. Okay? Same parity, thus 0. And so we're cool with that, things like that. We like it. So moving forward then, which if you want to reference this particular note, this is equation 6.26. We're cool there. The selection rule works out this way for the setup. Not always the case for all operators, but be aware this is a vector, so the negative side and all the other stuff we covered in the last few videos. So we can conclude with the selection rule that this is 0. This isn't that interesting though for what Griffiths wants us to do. So let's dive in, well, what Griffiths and Schroeder want us to do. So let's dive into part B. Now, in step number 2, part B, we need to get a throwback to what we covered in chapter 4. Okay, so bring back all those fun memories. And in chapter 4, we saw that n equal 2 was a degenerate state, at least for the energy levels. And at this energy level, there were 4 possible combinations of quantum numbers or states, which we see listed here. For n equals 2, you could have L equals 0 or 1, but if L equals 0, then M could be 0 or plus or minus 1. Excuse me. So we see that we have all possible combinations of states here. And so, based on how nasty or with the complex conjugates, all that other stuff, these two would not make a good choice of selecting, trying to make a new state out of. But we do want to have mixing L's as to not violate the parity rules or selection rules in this case. So let's choose these first two states and make a new state out of that. And in order to do so, we have to make sure that the new state is normalized as we have with all the rest of quantum mechanics. So that's where the 1 over root 2 comes from. Cool. We can do that with any two normalized states, add them together. When you take the complex conjugate transpose and multiply it in, you see that that 2 factor gets canceled, so we're good. All that fun stuff. But let's put this in the ket notation as to make sure that we're running the same process that we have in previous questions. All right, cool. So let's figure out the next step. And so to find the expectation value, we'll run through the same process, multiply the broad, which is in green, and the ket, which is in blue, sandwich it in between, and then we can apply the selection rules. So as you see, we get a double of root 2 and root 2, so they combine to 1/2. And when we distribute the 200 state with 200, we get this 200 with 210, 210, and all that other fun stuff with the multiplying, of course, you get that. But what we see here is that, again, by equation 6.26, we have something that is going to go to 0, okay? Because the selection rules tell us that they're going to go to 0. And because of this, let me get the pen out. We see that this L and this L match, and then this L and this L match. So we know that those go to 0. We like that. That's easy. If only we could have more zeros like that. However, we're still tasked with finding what the expectation value is based on this term and this term. So let's see how we do that. All right. So first things first, I think it'd be, do our due diligence here and clean up what this is actually asking of us in terms of the parentheses, which if we notice, instead of finding two expectation values of a vector operator, which is going to be 3 dimensions, so you're going to have three integrals for every dimension, so that's 9 integrals to evaluate, and having two of them, it'd be easier for us to use what we know about switching the order with the complex conjugates. Hence, double conjugate here will undo each other, but we can apply one of them to switch the order. And now you see you have a 2, 0, 0 state and a 2, 1, 0 state in this order. And then you have another one in this order. And if we remember from complex variables, well, this is just equal to 2 times the real part of the argument. Hence the 2 times the real part of this expectation value, which, as you might imagine, expectation values coming out real to the modulus squared will happen. So this is pretty good at saving us time. So we really only have one set of integrals to deal with. The integral with state 2, 0, 0 and 2, 1, 0 instead of 2 with 2, 0, 0 or 2, 1, 0 and 2, 0, 0. Nonetheless, clean it up now and we see that the 2's cancel. So we're left with just this expression to now solve, or equation to now solve. Let's get into that. Fair warning though, the selection rules tell us nothing about this particular expectation value that we need to find, so we need to calculate it. In doing so, we realize that the operator is a vector operator in spherical coordinates. So it's r hat, emphasis on hat, its unit vector tells us we have three different components that were broken down into Cartesian unit vectors, which we need to incorporate in these integrals. And this was covered in chapter 1 of Griffith's E&M as well, or you could look at the covers of the book. Not too bad, but be aware it needs to be brought in there. And now that we're dealing with P as the dipole, electric dipole as just a vector, not an operator, just a vector right now, we see that that is equal to QR, and R is equal to the magnitude times its unit vector. So this is why we have it in this notation. QR, and then all these other things. Now we can put this back in and see what we have. All right. So all that being said, we now have something that is in the X, Y, Z direction. So we have our three directions from the operator. And the integral itself, we see that everything we put in there is in terms of r sine or r theta phi, which is fine for what the state vectors were given in. So we could just use the D3 integral, i.e. the spherical integral. This is where the PDF will have all the tedious work behind it. And so look at that if you want more answers. But understand that psi of 200 and psi of 210 were found in problem 415 back in way long time ago. So go check those out. It is in the PDF though, so be aware. That being said, trying to simplify this, we saw that the normalizations for psi 210 and 200, which all of these integral sets have, and the fact that you have a q on every term, which is a scalar, can be brought outside. So you have q over 16 pi a to the fourth. Those are all on the outside of this bracket. And now each direction has its own integral set that we need to deal with. Okay, so here is the integrand simplified. Again, the PDF has all the simplifications in it. So now what we need to do is break this up and see how to integrate out all these parts. And this is the z component for one last clarity. But with the z component, notice that we don't have any arguments with phi, which will become very valuable here soon. Because we can use, forget the theorem's name, but nonetheless, we could split up this, Fubini's theorem, there we go. Because we can use Fubini's theorem since the integrand or integral limits don't have any arguments, we can split them up fair and square. Nice. One thing to note here is that in the x and y direction, the phi integral has an argument in it, and because it is a periodic function, cosine or sine, we see that the endpoints will cancel either evaluating to 0, 0 or evaluating to the same number, and with the minus sign in between, it cancels those to 0. So this whole x integral or x hat integral set goes to 0, and this whole y integral set goes to 0 due to this phi integral. That is awesome, and that's why we like looking at characteristics before we just plug it into a calculator. That being said, using something like Mathematica or Symbolab, highly recommend because we're here to understand the physics, not take 12 hours on integrals. That being said, the only one that really has anything to look at as far as evaluation is the z hat direction, so let's do that next. Alright, so as stated in summary, x hat and y hat both have zeros as their total due to the phi integral being 0 and multiplying everything by 0. Cool. So the phi integral now for the z direction yielded a 2 pi. The theta integral yielded a 2 over 3. Cool. And then we had to use the integral table at the back of the quantum mechanics book for the x to the n power times e to the negative r over a, which of course is the limits of 0 to infinity. Of course, we're looking at asymptotics here, so I don't mind using a table, save ourselves the time. The next part of this is just cleaning up this z integral section. So we see here that a and this one factor here will cancel. Let's note that 5 factorial is equal to 120. So this is equal to 120. And then, of course, dividing that by 2 yields 60. Taking a difference here, we get a negative 36. As you see, negative 36 is composed of 3 and 12, so factors of 3 will cancel. So let's continue the simplification. And thus we get a negative 12 here after we divide by 3, which of course now putting 4 pi into this gives us the negative 48 pi a to the 5th. But realizing now that we're in a way to, permanently show that since 4 pi, 12a, they're all real numbers, they're not complex, the real part of this argument is not needed, so we can drop it because everything in it is real. Cool, we like that. Next. Now in the next round of simplification, we see that 16 pi a4 can now cancel with everything in this bracket. Okay, 16 and 48 leave you with a factor of 3. Pi cancel with pi. All a4 here gets canceled with 4 of the 5 in this power here. So we're left with 1a. Not bad at all. Again, the setup is more trouble than the actual execution of this, and all those steps are in the PDF. But, since we're told from the question that this is an electron, we know that Q is equal to negative E. So if we plug that in, we see that we have a state which is non-zero, okay? So it's non-vanishing, and thus the value is equal to 3e to the a in the z-hat direction. And of course, this tells us that we have a state here, which is non-vanishing, which was the goal itself. So I'm sure you could find some other linear combination of these other of the 4 states that lead to a non-zero, and thus you could see how we can start seeing how certain state combinations might lead to uh, ways that we can have transitions and ways that we can't due to what levels are degenerate, yada yada yada. We'll see that more in chapter 11, I think is what he said in the text. But nonetheless, very important for us to realize that there's a handful of states in and of themselves that will lead to parity violations. Well, actually, all of them will due to the same parity, same L. So any combination of them, we might have overlap that's non-zero, and we're interested in those. So here's that. And with that, we'll go to concluding remarks and get ready for rotations. So, in summary, we covered how the specific selection rules for this operator applied and how much time that saves. And then we found how to find a state, which had to be a linear combination of things of the set energy level, came into fruition to a non-zero matrix element, which is very cool, or non-zero expectation value. Very important for us later, of course. Griffith, Schroeder, they put things in there now that we will run into later. And so just be aware that tally of things to keep track of keeps growing. This is only one such of the selection rules that's of big importance for us. But that being said, this takes a lot of work to compose, So a massive thank you to my supporters for making this possible. I'm extremely grateful for your support. And of course, if you find value in this content, please consider subscribing and sharing or even donating. That stuff all helps. I'm incredibly grateful for it all. And then if you want more, you can also become a patron for access to the supplemental material with this content, current and future projects, and one-on-one help, considering that a lot of questions are now being sent to DMs and things like that. It becomes very overwhelming to get everybody the attention they need when dealing with this and work. So be aware if you want more help there, it is available. New content is posted weekly to help fuel your curiosity, so please check in there because I'm constantly posting articles as I find them. That being said, books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. One method or the other will find a way to get in contact. As always, thank you for watching, and until next time, stay curious.